Okay, more limits problems, but these are really disguised rational functions problems. So for number 40, for what values does the function have a removable discontinuity? What you want to look for is factoring and what you can cancel. So if I take x squared plus 4x minus 21, two numbers that multiply to negative 21 and add to 4 are positive 7 and negative 3. Okay, same thing with the bottom. Multiply to 21 and add to 10, so that's going to be all positive. Positive 7 and positive 3. So my term that's going to cancel is the x plus 7, which means that x plus 7 is equal to 0. Subtract your 7. Our removable discontinuity happens at x equals negative 7. If you needed to find the y-coordinate of the removable discontinuity, what you do is you take your reduced function, x minus 3 over x plus 3, which is the only difference between your original function and your reduced, is that it fills in this hole, and put in your negative 7. That's how you would find that y coordinate if you needed to look for it. We didn't on this one, but I just wanted to make sure that you had the information. All right. Here we have a piecewise function. Really, it's just a removable discontinuity that's being filled in here. So which of the following is true? The limit exists, f of 3 exists, and f of x is continuous. Well, from the beginning, we know f of 3 exists. If we're looking at this function here, at x equals 3, f of x equals 1. So we know that 2 absolutely is true. For the limit, since we're basically filling in this hole at 1, we know the limit is going to exist. We have a removable discontinuity here, and if you're not sure how I knew that, take a look at x squared minus 9 over x minus 3. X squared minus 9 is the difference of squares. So just like the problem before, you have a removable discontinuity at 3. So the limit is going to exist. This whole thing is doing the same thing from the left and from the right. We just need to know, is that hole being filled in? Is the y value 1? So we know that this guy is true. We know that 1's true. We know that 2 is true. Let's see about 3. For f of x to be continuous at x equals 3, when we plug in 3, we've got to get out 3. Well, if we look at when we plug in 3, we actually need to get out 1, because that's how our hole is being filled in. If we look at this guy, our reduced function, the hole would fill in at 3 plus 3. If it filled in at 6, we would have a continuous function. So what's happening here, if you graph this on your calculator, and I know I said this is on the no calculator section, but you can take a look at it. What this is this a line with a slope of 1 that goes through 3, y equals 3. This guy would be 6, but it's filled in down here at 1 by this piece. So we're not continuous, so only 1 and 2 are true. All right, let's take a look at 42. A similar problem here with 42. Go ahead and pause and see if you can use what we did on the last problem for this one. All right, hopefully you had a chance to look at that. I'm going to take this in pieces here. First, I'm going to go ahead and look at this. This means that f of 9 is 18. So f of 9 exists. True. The limit as f of x, or as x approaches the limit of f of x exists. Well, let's work with this. Let's find the limit, which we didn't do quite so directly last time. The problem with taking this limit is that denominator, so I'm going to work what I can to cancel it here. Since I factored, I can cancel my x minus 9s, and now I'm just taking the limit as x approaches 9 of x plus 9. When I plug in 9 there, my limit is 18. So the trend of this guy is 18, the limit is 18, the actual value is 18. If the limit and the actual value both match, then your function is continuous at that x value. All right, we'll stop there for this video.